Hi everyone, it's Miss Peterson. I just wanted to walk through the specific heat lab with you and go through some specific examples um, so that we're all on the same page as to what is expected for this lab. I know there is a lot of data collection that was required here, and you had to interpret your data as best as possible with limited assistance from us. So I want to do one example of copper with you. So hopefully you're on the right track. But what we're doing in this lab is called calorimetry, which is basically a procedure used in chemistry, food science, things like that to show how energy or heat gets transferred from object to object. Now I said food science. So food scientists can use this process to figure out how much energy or to figure out how many calories are in the foods that we eat every day. Now they have a way more sophisticated version of this calorimeter. So hard to say in their labs, but it works very similar with minimizing the heat loss that we might see in this example. So your definitions for your pre-lab should be no problem. The first part is figuring out the masses of our samples. So over here, hopefully you can see both of my screens, but this tells us that the mass of our empty container, our foam container, is 9 grams. So as you can see over here in my Google Doc that I wrote in 9 grams. So hopefully you have that visual to better understand this. Now it's going to go through and tell us the mass of all three of our samples. So starting with copper, we have 62 grams. Moving on to iron, 174 grams. And then my last one is the rock, which should say 98 grams, right? So I've got my 3 sample masses listed in there along with the mass of my empty foam container. I think everyone was able to successfully identify that. But the next part is figuring out initial temperatures of the samples. In order to heat up our samples to be real hot, they were all plopped in this boiling pot of water, and then all of their temperatures are going to reach the same point, which is about here. This is what I used, and I know it beeps in a second. I'm just going to go with my numbers that I used initially. So all 3 samples have an initial temperature when heated up in that boiling pot of water to be 98.2 degrees Celsius. All right, moving on. Now I'm just going to focus on copper and use that example, and then you can figure out the rest for iron and rock after that. But basically, he takes some of that water and puts it into the foam cup. We need to remember that the foam cup is 9 grams. So in order to figure out the actual mass of the water, we're going to take 192 and subtract 9 grams from it. So that's 183. You can check my math on that. Now he's figuring out the initial temperature of the water, which was listed there. That went kind of fast for me. Beep. But there it goes. 19.4 is the initial temperature, degrees Celsius, of the water for our copper sample. And then the last part is he's going to plop in the copper sample into our water, and that hot copper is going to transfer its heat to the water because heat flows from hot temperatures to low temperatures. And we know we've got a nice scalding hot sample of copper, and it's going to transfer its heat to the water. In order for us to get a good final temperature reading for those 2 samples, you have to mix them together, swirl them around, shake them around so that it can reach what is known as thermal equilibrium, or when the heat between two objects balances out and it becomes even. So we can see there's some readings here with this temperature probe on his computer, but I like to keep things consistent, so I'm going to use the yellow laser readings that he gives out throughout the lab. Again, just for consistency piece. So he's swirling it around, trying to reach thermal equilibrium. Eventually it'll get there. The other two samples take a little bit longer, so be patient with figuring out the final temperature. But here we go. This thing should load any second now. He's going to take the laser thermometer, and as close as we can possibly get to that, 21.2 is going to be my final temperature reading for the water and the copper sample. Okay. Next up is going to be figuring out some calculations. So I'm just going to scroll a little bit so you can see what I'm doing and have that reference point again. Data for the iron and data for the rock go in the same order of what I just walked you through. It just takes a little bit longer to figure out that final temperature, so be patient and, do your best to pick whatever recorded temperatures you think are necessary. I want to talk about this calculation, which looks totally different from what we see in 9.1 notes, but it's actually not that different. So don't be afraid of it. I know that's small, but you have your own version you can reference. Q stands for how much energy is being gained by the water. Okay, so that's what we're solving for. All of this information that we're plugging in is going to be info on the water. So if I look at my data table, I'm specifically focused on the water data. I'm taking the mass of the water, which was 183. Hopefully you can see my mouse highlighted over here. So that's the mass of the water. The specific heat, I'm going to use this one that's listed on the data table in our Google Doc for my calculation, just because it was there when I was doing this lab. So 183 times 4.18. And then I need to figure out the change in temperature. And this is for my water. So this is my final reminder that the final temperature of my water up here, 21.2. And this was the initial temperature, 19.4. Oops. So if I subtract these two values from each other, then multiply that by, again, 4.18 times 183, I should end up with an energy value that is somewhere around 1,376.89 joules. And that's saying how much energy the water gained from that copper object. Okay, next up is figuring out specific heat for my sample. And a specific heat is telling me the amount of energy needed to increase the temperature of any substance by 1 degree. And it depends on the type of material. Some are really good conductors, so they have low specific heats, and then some are really good insulators where they hold heat where they originally were, so they have high specific heats. So I'm going to figure that out for my copper sample here. Q is what I just calculated and the energy gained by the water. So I'm taking 1,376.89, and then I'm going to divide it by the information that goes with my sample, with the copper information. So I'm going to take the mass of that copper, which was 62, and then multiply that by the change in temperatures. Here's my final temperature for the sample, 21.2. This was the initial temperature of my sample, 98.2. So if I take those two temperatures, 21.2 minus 98.2, multiply by 62, which was the mass of my copper, and then divide that value into my thermal energy here for copper, I should end up with a number that looks like 0.288. And it technically is negative, right? If I do this calculation correct, I'm going to end up with a negative specific heat. I'm just going to ignore the fact that it's negative. It's giving me some information because the temperatures, the final temperature is lower than the initial temperature. That's why it turns negative. So really I should have like the absolute whatever those things are called in math, that should be surrounding it. So I'm just going to take the positive value that goes with it. Okay. Last but not least is how far off was I from the actual specific heat of copper, since that is a known thing. So if we look at this video again, here we go. I'm going to hide that. It tells us here the actual specific heat of copper is 3.84. What I calculated out to be was 0.288. I want to figure out how far off I was in my experimental calculation to its true value. So I'm going to use this 0.384 as the actual number that goes into this equation. Subtract by what I just calculated, 0.288. Divide by the actual number again, and then multiply that bad boy by 100, and it should tell me that my percent error, I think, is somewhere around 24.5% off, which isn't too bad. I did the other samples, or the next one, iron, and had a very large percent error, and that's okay. No judgments on having some large percent errors. It just probably means you read the final temperature of your water and sample incorrectly or at the wrong time, and that's fine, but there is also lots of sources of error that can be found in this lab too. So hopefully that gives you an idea of what you are expected to see. And again, there is some differences that you could have in some of the initial temperatures and things like that. Just take your time with the videos. Be diligent about picking out good data, and you should be just fine. I'm going to extend this assignment to Saturday for those of you that want to go back and redo it. Sorry, it took a little while for you to figure it out, or it took way longer than any other assignment. So extend it to Saturday. You can redo it, or if you already submitted it and you're like, fine, whatever, I'll give you your feedback. You can always go back and change some of your data, fix it up, and resubmit it for full points. So that's on there. Tomorrow you have 9.2 notes and section review questions to do. And Monday is your test for chapter 9. So it's a very quick turnaround from our last one. If you have questions on anything, please reach out to me so I can help you out. I know the specific heat stuff can be tricky, but really you should just know how to fill in an equation when you're given it all the data for like the energy equation that you see in the 9.1 notes that Mr. Pressler goes over. So that's the only real calculation you have to get into if you're concerned about that. Again, chapter 9 is much more difficult, in my opinion, than chapter 8. And that trend is going to continue for all of our following chapters. So please make sure you're pushing yourself and trying to understand the material to the best of your ability. And if you don't feel comfortable, reaching out to ask a question that you might feel silly, there's lots of resources, science resources out there, videos, whatever. But hopefully you feel comfortable asking any sort of question. And I hope that helps a bunch and gets you right back on track for what you were working through on this lab. Let me know how it's going. Okay. All right. See you later.